Welcome back to The Explainer, everyone. I am absolutely thrilled you're here today because, well, as we follow the structure outlined in our source document today, titled ENGV, we're doing something a little different. Instead of looking at just one isolated concept, we're diving into one single magical date on the calendar, June 4th. This is, literally, a golden day in math history. I mean, it is incredibly rare to find a single day that ties together so many brilliant minds spanning entirely different centuries and continents. So let's just jump right into this and see how a few people connected to this exact date completely revolutionized the modern world. But before we get to the people, let's take a look at your everyday life. Think about this for a second. How does your smartphone manage to stream crystal clear audio on Spotify or Apple Music, even when you've only got like a single bar of cell service? What actually makes that signal compression possible? Or how about this one? When you're driving through a complicated, winding mountain pass, how does your GPS instantly calculate the single fastest route out of thousands of overlapping possibilities? It kind of feels like magic, right? But the secret powering these everyday miracles, it isn't magic at all. It's abstract mathematics. And that brings us right back to our timeline. There's a hidden thread connecting these questions. The mathematical foundations for your GPS, your phone's signal processing, and even tomorrow's quantum computers, they were laid by four incredible visionaries who all share the exact same birthday, June 4th. So let's start with our first profile and travel way back to 1891. Section 1, The Mountain Guide. Let's meet Leopold Vietoris, born in Austria on June 4, 1891. This man's life literally spanned 3 different centuries. He lived to be almost 111 years old. And he definitely didn't just sit in a dusty classroom. He was a man of action, and his life directly fueled his mathematics. Just look at this incredible resilience. During World War I, Vietoris volunteered for the army, was severely wounded, and then actually served as a military mountain guide in the Alps. He even spent 9 months as a prisoner of war in Italy. And, the extreme terrain of the Alps and those geographical challenges he faced, they profoundly shaped his thinking. He was out there in the freezing mountains, thinking about complex geographical spaces and abstract geometry. Which leads us directly to his greatest contribution. While most of us would honestly just be focused on survival, Vietoris was out there dreaming up the Mayer-Vietoris sequence. Now, in plain English, what is that? Well, it's a brilliant mathematical method in algebraic topology. It basically allows us to take impossibly complex spaces, think like an entire mountain range or a massive 3D digital landscape, and compute their properties by splitting them up into simpler, overlapping pieces. And this brilliantly illustrates exactly why abstract math matters. Vietoris didn't leave his math on the blackboard. He used it to hold a patent for aerial mapmaking, he modeled how glaciers flow, and he even applied differential geometry to figure out the physics of alpine skiing. So the crucial takeaway here is this. Every single time your GPS breaks down a complex, real-world map into simpler chunks to find your route, it is relying on the topological concepts pioneered by this Austrian mountain guide. Section 2. Overcoming barriers. Let's jump forward exactly 75 years on our timeline to June 4th, 1966, to meet our next brilliant mind, Ukrainian-born mathematician Svetlana Jitomirskaya. Now, you might assume she was a math prodigy from day one, right? But consider her own words. She initially wanted absolutely nothing to do with math. Her mother was a famous mathematician, and seeing the intense pressure of the field, her mom actually steered her away from it. Svetlana wrote prize-winning poetry and fully intended to build her entire life around Russian literature. But her path was forcibly changed by the realities of the era. She faced systemic discrimination in the Soviet Union, specifically strict anti-Jewish quotas at Moscow State University. To have any chance of getting into a humanities program, the odds were, well, nearly zero. Math offered a slightly better chance of acceptance, but she still had to obsessively prepare for notoriously hostile oral exams that were basically designed to keep her out. Ironically, though, it was this intense, unfair barrier that accidentally sparked her deep, lifelong love for mathematical problem solving. And thank goodness she found that passion, because she went on to completely revolutionize the field of mathematical physics. She's best known for her work on quasi-periodic operators. I know, that sounds like heavy jargon, but think of it this way. She models systems where there's this breathtaking, beautiful competition between complete randomness, so chaos, and perfect repeating order. Her work solving the Aubrey-Andre conjecture was so groundbreaking, it actually won her the prestigious Satter Prize. So how does this actually translate into the real world? Why do we care about quasi-periodic operators? Because they are unlocking the quantum universe. Her equations help explain the integer quantum Hall effect, they model bizarre atomic structures called quasicrystals, and they form the absolute bedrock of quantum chaos theory. Your big takeaway here? When quantum computers finally become everyday technology, it's going to be thanks to the foundational order Svetlana found inside the chaos. Section 3, Visualizing Algebra. Staying on that exact same day, June 4th, 1966, we shift from a Ukrainian-born pioneer to a Russian-born powerhouse, Vladimir Voevodsky. Voevodsky tackled some of the most dense, abstract concepts in human history, which earned him the Fields Medal, that is basically the Nobel Prize of Mathematics. His monumental achievement was developing something called motivic cohomology. Now, for the non-mathematicians watching, what he essentially did was build a bridge. He created a way to connect the flexible, geometric world of shapes and spaces with the rigid, symbolic world of algebraic equations. I absolutely love how he put it in his own words. He said it gave mathematicians a fantastic way to translate visual geometric intuition into hard algebra. He actually proved the 30-year-old Milnor conjecture simply by realizing that we can use the visual parts of our brain to solve non-visual abstract problems. It's just a really powerful reminder that math isn't just numbers. It is literally a language for visualizing the invisible structures of our universe. Section 4, Special Functions. Finally, let's jump back slightly on our June 4th timeline to 1933 to introduce Richard Askey. If Voevodsky was the visionary architect, Askey was the master mechanic. Askey devoted his entire career to something called special functions. Unlike some mathematicians who love theory just for the sake of theory, Askey was all about utility. Special functions, like orthogonal polynomials, are highly specific formulas that act as a toolkit. When an engineer or a physicist hits a brick wall trying to solve a really complex real-world problem, like how heat dissipates in a microchip or how sound waves compress, they literally reach into Askey's toolkit to find the exact mathematical tool to crack it. This quote brilliantly illustrates his entire philosophy. He didn't care about making things complicated. He cared about making them work. His mastery of these practical tools even helped other mathematicians solve the massive Bieberbach conjecture. So the next time your phone successfully compresses an audio file so you can listen to music on a really weak internet connection, you can thank Richard Askey and his toolkit for that. Section 5. The Pattern of Progress. Connecting the dots. So what do all of these incredible stories tell us? Let's bring it all together as we wrap up this explainer. When you look at this comparison, the contrast is absolutely striking. On the left side, we have the messy human experience. Leopold Vietoris surviving the trenches and avalanches of World War I. Svetlana Jitomirskaya fighting past systemic prejudice and anti-Jewish quotas. You have shifting borders and changing passions. But on the right side, born from that very chaos, we have the mathematical reality, the discovery of perfect order, unifying symmetries and universal truths. These incredible people took the turbulence of their lives and translated it into the beautiful, enduring logic that literally powers the technology we hold in our hands today. Which leaves us with one final, really exciting thought. If these 4 individuals, all born on June 4th, could pull so much order out of the chaos of the 20th century, what hidden patterns in today's chaotic world will tomorrow's mathematicians uncover? Keep looking for the math all around you, because trust me, it is everywhere. Thank you so much for joining me on this explainer. Don't forget to engage with the concepts we talked about today, and I will see you next time as we continue to make math easy and fascinating.